which generalize the well-known in hydromechanics scalar tensor tension, scalar tension on the case of a solid body. This surface effects allows to describe size effects which are observed for nanomaterials. Now, in this work, we use the Gürten-Murdoch model once again to describe the surface effects. The system of Gaussian equations for nonlinear elastic bodies with surface effects in the absence of body forces consists of the equilibrium equations in the volume, equilibrium conditions on the part of the body omega s where the surface stresses are acting, the constitutive relations for the bulk material and for the surface, and geometric relations. Here, by S, we will denote various quantities related to the surface, and, well, without indices will be quantities related to the volume of the body. This is the Nabla operator, 3D Nabla operator in Lagrangian coordinates. This is the surface Nabla operator. D is the Piola stress tensor, P is the Kirchhoff stress tensor, G is the Cauchy-Green strain tensor, C is the deformation gradient, and R is the position vector in the actual configuration. Now, in the case of in the general case of an isotropic compressible body, the strain energy density W can be expressed as a function of the eigenvalues of the Cauchy-Green strain tensor, and this allows us to derive the expression for the Kirchhoff stress tensor in the following way. Here, gk and dk is the eigenvalues and eigenvectors of the Cauchy-Green strain tensor, and for the surface we use the following representation for the constitutive relations, where J1 and J2 are the two invariants of the surface strain tensor. Now let's consider our body. We'll study the stability for a circular rod of length L and radius R0. It's subjected to axial compression and possibly external pressure. And we assume that on its lateral surface, the surface stresses are acting. Now, the deformation relations for this kind of deformation written like this. Here we have one parameter. Right now it's an axial compression ratio, and there is also an unknown function f, which describes the radial deformation of our rod, and which is determined from the equilibrium equations and boundary conditions. Now, for this kind of deformation, the expression for deformation gradients and strain tensors are relatively easy, and as you can see, the eigenvectors for the strain tensor coincide with the basis vectors of the cylindrical coordinate system. Due to this, we can express our stress tensors for the bulk material and surface stress tensors like this, and our system of equilibrium equations reduced to only one scalar equation for the unknown function, and our boundary conditions we express like this. Here the second term is due to the surface stresses, and the third term is due to the possible external pressure, which is calculated per unit area of the deformed rod. Now, to find the unknown function, we also have to demand one additional condition, namely the absence of tear at the rod axis, which will look like this. it's quite natural. So in general case, to determine the unknown function f, we have to solve this boundary value problem for a given strain energy density functions for the bulk material and for the surface. In a more simple way of homogeneous material, the unknown function will be linear, with the constant to determine from this equation. Now let's assume that to study the stability of this initial strain state, we assume that there exists a small perturbation of it under the same loads, which differs on a small perturbation vector. The linearized equilibrium equations and boundary conditions which describe this perturbed state, in general case written like this. Here, this is the linearized conditions on the lateral surface, and this one is the linearized conditions on the rod ends, which express the absence of friction and given normal displacement. Now, to determine the linearized Piola stress tensor, first we have to find the linearized Kirchhoff stress tensor, which is done by linearizing the constitutive relations. Thanks to the fact that the Kirchhoff stress tensor and Cauchy-Green strain tensors are coaxial in the isotropic body, and also due to the fact that eigenvectors dk and linearized eigenvectors dk dot are mutually orthogonal, this allows us to express all of the components of the linearized Kirchhoff stress tensor in the basis of eigenvectors dk through the components of the Cauchy-Green strain tensor, like this. And a linearized Cauchy-Green strain tensor can be relatively easy found directly. In a similar way, to determine the linearized surface stress tensor of Piola type, we have to carry out the linearization of the surface constitutive relations, which is a more simple task, and it's done like this. Now, our linearized equilibrium equations is a system of three differential equations in partial derivatives, which depends on three unknown functions, which are components of the perturbation vector. Using the following representation, solution allows us to separate the two variables phi and z in these equations, and it also allows us to automatically satisfy the boundary conditions on the ends of the rod. As a result, the stability analysis is reduced to solving a boundary value problem for a system of three ordinary differential equations, which of course is a more simple task. For its solvability, we must formulate also some additional conditions, which follows from the assumption that the unknown functions and their derivative are not infinite at the rod axis. This is these conditions for the symmetric buckling mode and for the bending buckling mode. Now our linearized boundary value problem is complete, and we can study the stability of our rod for a given material model. Further, I will discuss some results of numerical simulations which were obtained for an aluminum rod in the case of a simple axial compression. We used here two models for the bulk material, namely the harmonic model and blades and core model. In case of blades and core model, we consider two limiting cases. If first case is when B is 0, which leads to the absence of this term in the strain energy density. And the second limiting case, as you understand, is B equal to 1, when the second term vanishes. So we can see that we effectively considered 3 models. And for surface material model, we use this simple quadratic representation. Now here, lambda and mu is the classical lemma parameters, and lambda s mu s is the so-called surface lemma parameters. This is the way of these parameters for the aluminum. And also we introduced, for convenience, some dimensionless parameters. This is relative axial compression, this is relative radius, and this is the length to radius ratio. Now, we studied how the overall size or the scale of the rod affects its stability. It's quite well known that in classical elasticity, if we consider the stability of rods which have the same length to radius ratio, then the critical values of axial compression for this rod will be the same. For the reference purpose, the value of this critical compression is denoted by dotted lines here. And here we have results for, by solid lines, we denoted the results for the rods with surface stresses. As the size parameter, we use the relative radius. And, well, as you can see, with the decrease in size, the stability of the rod increases. Of course, this effect is negligible at macroscopic dimensions, but for micro and nano size, especially for the nano-sized rods, it's quite significant. Qualitatively, the same results was obtained, and the previous result was for the harmonic materials. As you can see, for blades and core materials, results are almost the same. On the values is different. And here we have a comparison of results for different models. Generally, the results for blades and core model are the rods for blades and core model are more stable, but with decrease in size, the difference becomes less and less apparent, which can be explained by the fact that for the nano-size rods, the influence of the bulk material became less important, and a major role plays the behavior of a surface. So, as a conclusion, we can say that is once again confirms the importance of taking into account the surface effect, in this case during the stability analysis for the bodies at micro and nano-sized scale. Well, that's all what I wanted to speak about. Thank you for your attention.
Questions? I think it was your slide 13 when you have material parameters.
Oh, well,
the surface parameter specific.
Yes, I can give you the exact reference if you wish. It was no. Regrettably, I do not have any equipment.
My second question is, I think the surface parameters that are available for aluminum, they are only for smaller strain. Your model was fine for making. And also there is a third parameter.
Maybe, but in this case, maybe if I consider a more complex model for the surface behavior.
You can send me
But here I started, as I said, a quite simple model for the surface behavior. Of course, we can use a more more complex expression here. And then you can, of course...
I have no problem with the model itself, but I think the parameters from experiments that are available are not fitting to this model yet. So,
well, maybe.
Okay, if